So I realized that last little piece of the video cut off my handwriting. So again, looking at converting 60 degrees into radians, we just set that up as a ratio of 60. What piece of pi over 180 is that? And we get pi over 3. Also, this canceling out of this r basically means we're taking this equation, this s being equal to 2 pi r, we're putting it into the 2 pi r over r, so we're putting it into this equation here. So that's sort of, these r's cancel, that's how we get to that 2 pi. So hopefully that clears that up a little bit from the last portion of the video. And moving on from that, I do have some more information on how the radian becomes important in using these things, but in the interest of saving time, I know some people are just gonna be like, yeah, we'll just use radians and we'll go with it, and they're good. If you have any other questions, it might be a good place to start with your questions for class next time. So check your answers here. The one that I want to go over with you is this idea of two circular motions are being seen to be completely out of phase. So in other words, that would be the same as if you sort of reasoned your way through that, looking at maybe bug on record A and bug on record B. If they're completely out of phase, that means that they're totally opposite. So that means if this bug A is at this 90-degree position here, then that means that this bug down here would be at this 270-degree position, which would mean they would be 180 degrees out of phase. So 360 degrees would be perfectly in phase with one another. So perfectly out would be 180 degrees. And then they say, okay, well, what's that value in radians? Well, 180 degrees is pi radians. So hopefully just thinking about what that idea of what out of phase might mean, especially saying totally opposite, but hopefully with that explanation, that helps things along a little bit. So moving on. We're going to talk about angular velocity really quickly, also known as angular speed and angular frequency. And it's not how many meters per second that particular rotation occurs through. That would be a translational or a linear description, right? Meters per second is translational because that's in meters. But if we talk about it in radians per second, now all of a sudden we're talking about angular velocity. So this measurement for angular velocity, it's this little guy, this little curly QW, and it's an omega. It's the lowercase omega. And that is given by delta theta in radians, right? So that's in radians, divided by the amount of time. So just like with translational motion or linear motion, we have displacement divided by time. This angle here is angular displacement. So it's displacement divided by time. It's not any different. It's just so happens to be moving in a circle and we're measuring in radians. That's the only thing different about it. So again, if we want to kind of hash some of these equations out and try to create some new equations from this particular original equation, we can say that one turn is 2 pi. So also omega can be equal to 2 pi over the period, time t. And because 1 over the t is frequency, we can kind of plug frequency into that equation and we can spit out omega being equal to 2 pi times the frequency. You can go ahead and derive that on your own, or just trust that that's what that is. All of these equations work, but I want to point out to you guys that these equations are not in the data booklet. So take a few seconds to pause the video and try this particular example. If the object completes 20 rotations in 34.6 seconds, calculate the frequency and the angular velocity, hit pause, see how you do. On your mark, get set, go. And coming back, hopefully you got, for the frequency, 0.578 hertz. And I did 0.578 because we have 3 sig figs here. And the angular velocity, taking that measurement of frequency, the most convenient place to plug that in is into 2 pi f. And so I just plugged it into 2 pi f. Could you have done it a different way? I don't even know if you could have. Well, you could have taken the opposite and done your period and divided it by 2 pi and gotten the same value. So that would be 3.63 radians per second. Don't forget, you gotta be in radians. So moving on from that, there is a relationship between the speed of the mass undergoing circular motion, velocity, and its angular velocity. So this again is linear. This here is rotational. So what is the relationship between the linear velocity and the rotational velocity? So basically what I want you guys to remember from this is we say if a point is in circular motion with a constant linear speed, it also has a constant angular velocity. So think about that. If a point is in circular motion, so something moving around in a circle, with a constant linear speed, it also has a constant angular velocity. So there is a relationship. So we know that velocity would be distance divided by time. So that would be 2 pi r divided by t. And omega is equal to 2 pi over t as given by that equation up here. Ting. So if our angles are in radians, then we can set those kind of equal to one another. We can play some math and we get that our linear velocity is equal to omega, that angular velocity, times the radius. So those are kind of the basics in terms of just velocities. Moving on, we're going to kind of talk a little bit again about centripetal forces, a little bit of a review of that. So basically, we talked about when an object that's in a circle speeds up, or if the radius shrinks, the acceleration needs to be a little bit larger. And that would be kind of that force being exerted, or that centripetal force. Remember, that's a center-seeking force. So everything that, as that velocity tries to move in a linear way, that centripetal force is going to pull it back and keep it in that circular motion. So again, why would a satellite not need an engine to keep it moving? Well, because gravity is acting as that centripetal force. So now talking about centripetal force, if there's a force involved, there's got to be an acceleration, because force is equal to mass times acceleration. We don't get to forget those rules just because we're dealing with rotational motion. So the equations that we have for centripetal acceleration and centripetal force, and these are the ones that we're going to be using as we work through some of these practice problems, is that your centripetal acceleration, and you can give yourself that little CEN designation down there so you know whether you're talking about linear acceleration or centripetal acceleration. That's going to be equal to your velocity squared divided by r. We can take and break out that velocity and plug in the old equation to it and divide that by r, and we square that, and now we get 4 pi squared r over t squared. It is derivable. You can get this from the other equations. I'm not going to get into it. I just want to give you guys the equations so that we can get some practice going. So now if we want to talk about what that centripetal force is, this is our equation for acceleration. So in order to get acceleration as being, or force being mass times acceleration, all we have to do is multiply mass by the top. And so hopefully you guys got that. In linear, force is mass times acceleration. In circular, force is also mass times, here's your acceleration right here, v squared over r, which shows up right here. Or we can say force is equal to mass times omega squared r. It's another way to, omega squared r. Just another way to load that dishwasher. So centripetal force is going to be equal to mass times velocity squared over r, or mass times omega squared over r. Remember that omega value is in radians. So far, so good. Okay, and we'll move on to get some examples and some practice problems. We can take a look at how this kind of plays out in some other situations.